indexed by the elements of X, where X is a set indexed by 1 to up to N, and Y 1 to up to P. The two sets are there. So we are having a matrix M with N rows and P columns, and which are indexed by the two sets X and Y. Let subset of X and beta be a subset of Y. Matrix of X are indexed by elements alpha beta. So M of alpha beta, this one is a subtext of the origin and whose by beta is equal to beta. Note the same submatrix by M alpha. If Y, if that means whole set Y, then we can denote the matrix by M alpha column, and similarly to X. So this is the usual one. By P transpose, we denote the transpose of the matrix P, and by X complement XP, we denote the complement of the set X. Spectrum of the matrix A is denoted by spec of A, and J M by N is the all one matrix of order M by N. That means whose all entries are one matrix. Now come to the actual fact, the equitable partition and quotient matrix. Consider a square matrix A. The columns are indexed by the elements of X M, and whose are 1 to up to equal to 1 X M. Partition, we have set A is the N whose column indexed by the, and I is the partition of X. That means X1, X2, M all are subset of, and union of X2, Xm. The character C equal to of by M order matrix, such that Ci1 if I belongs to Xj and 0 otherwise. So this matrix actually helpful for some of the computation part. I will show you where we can use this one, characteristic matrix. So actually its entries are either 0 and 1, and it's an n by m matrix for the pi. We partition the matrix A according to pi. So it's a part. The whole matrix A was there, and we partition it into block form in this way: A11, A12, A11, like this. And where A to A the 1 is a matrix whose index by x1 A12, this block A12, these rows are indexed by the set x1, set x2. In this way, we have partitioned the original matrix A by M block form. Now, if Qij denote the average row sum of the block Aij, that means what we are taking Qij, another is that Qij is the average row sum of the block Aij. Then, in this way, we can have M into M number of Qij equal to the quotient matrix of the A. average row sum of each of the block A1 to A1, and these average row sum are Q11, Q12. Yes, sir.
Hello. This average
Hello.
row sum you need to define.
Average row sum is suppose. Okay. Average row sum. Suppose a matrix have m number of rows, and each row has some sum, right? That suppose this is a matrix. I'll come out with some examples, right? So maybe there I can also define more precise.
Yeah. Okay.
Wait. So basically, take the row sum of all the rows, make the average. Come up with the equivalent. Now, make the quotient matrix Uij. Now, if the row sum of each block Aij is a constant, then the partition pi is called equitable. What does it mean? That means, suppose consider the one, and we have partitioned the matrix in such a way that the block A11 have all the row sum n. Right? Again, the block A12 may be different. Within A12, all the rows sums are same. Case for all the block, then we can say the partition pi is equitable. I will come up with the example and understand very clearly. I think it is visible to all of you. The whole matrix.
Yes.
Are you all this?
Yes.
You understand the fact. Can you see that there is suitable? Can one of you respond it? Suppose first, if we just take the definition, we can compare with the definition. The whole matrix A is a square matrix of order 6 by 6. Its rows and columns are indexed by the set capital X equal to 1 to up to 6, because it's a 6 by 6 matrix. Now, my question is, we can partition the matrix in such a way so that we can able to get a equitable partition for the matrix. So we can partition the matrix in block form, where each block have some constant row sum. Can anyone of the research scholar respond this? What is that partition? One hint is, okay, we can have three partitions, x1, x2, x3. What we to do, we have to find a partition in this kind of block form. It may be one, some cases it may be one, some cases that does not matter. Hint is the first set X will contain one element.
Yeah, I think
Yes.
if you take the first element, that will be the A11 block. Then the
Right.
A22 block will be the next 2 cross 2 principal block, that is having 2, 1 and 0, 3.
Exactly.
And then the last is the 3 cross 3 block. Yeah. A33 is 3 cross 3 block.
Can you see our partition? The matrix A.
Yes.
See that we have that matrix A whose rows and columns are indexed by the set 1 to 6. Now can that is 2 and answer it is a constant. So we don't think much. I think that A211 block, it has constant row sum. See that the one element which is -1, second row is also having only one element which is -1. The next block A22, it has two rows, 2, 1 and the second row is 0, 3. And if you take the row sum 2, 1, this is 3. Again, if you take the row sum, this is again 3. So it has constant row sum, right? Similarly, if you see all the blocks, all of them are having constant row sum. Now, as in some of you asked now that please define what is average row sum. Now, in that this matrix is it's that we can have this all the case it is the constant row sum, but it may not be this for all, right? Maybe in some cases this block have row sum 4. Thus, if first row sum is 4, the second row sum is maybe 7. Then we can just add 4 plus 7 divided by 2. That will be the average row sum for the whole block. Okay. Similarly, we can find the other block row sum. So till now what happened for this matrix, we can able to partition the matrix in such a way that each of the block will have constant row sum. This much is clear, right? If something is not clear, please stop me and now we will find our quotient matrix. As we said, that will take the constant real sum of the each block. So A11 block is the 1 block. So Q11 is 2. That's why it's a Q is 2. Q11. Row sum -1, so it is -1. This is 2. In this way, all the constant row sum we have taken and we formed it Qij, and we form the matrix Q equal to Qij. Here the partition, as the matrix have this kind of situation, so the partition phi for the set X, and for the case of this matrix A, we called it as a equitable partition for the matrix A. So equitable partition of the matrix is clear. We will have some more example also. If you have some question, you may ask. Now, what is the benefit of this kind of partition and the quotient matrix? The first very good and useful result is, you can find it in Brouwer's and Hammer's book, that if Q be a quotient matrix of a square matrix A corresponding to an equitable partition, then the spectrum of A contains the spectrum of Q. What does it mean? So we have an original matrix A, and it has an equitable partition. From that, we find a quotient matrix Q, a 3 by 3 matrix, because we had three partition set. All means if the partition set have three subsets. Now that result says that all the eigenvalues of the small matrix Q is also the eigenvalues of the original matrix. Okay. Sometimes this result is very much useful. In my PhD work, I have used this result in many places. So all the eigenvalues of the smaller matrix, that means the quotient matrix Q, are also the eigenvalues of the original matrix A. And now you may have some question that this matrix Q is a 3 by 3 matrix. The matrix A is a 6 by 6 matrix. What about the other matrix? Other eigenvalue we cannot say from this result. But the matrix Q is a 3 by 3 matrix. So all the three eigenvalue of the matrix Q are also the 3 eigenvalue of the matrix A. This much is clear. Next, in 2018, me and with my guide, Professor Pratima Panigrahi, we did a result, and it says that spectral radius of a non-negative square matrix A is the same as the spectral radius of a quotient matrix corresponding to an equitable partition. What it says, that if negative matrix A, for this example, it is not a non-negative matrix. Non-negative matrix means, I want to mean that all the entries are non-negative. Although it is not, but it's non-negative, and we have a equitable partition, and we have a quotient matrix corresponding to that equitable partition, then the spectral radius of the quotient matrix Q is the spectral radius of the original matrix Q. Now, what is the significance of that? This result is also very much useful to find the spectral radius. In some cases, your original matrix may be very large one. But you can able to partition the matrix A, the original matrix, by taking two partition sets. Then in this case, your quotient matrix will be of order 2 by 2. Then it's very easy to find the spectral radius for the smaller matrix Q of 2 by 2 order. And that spectral radius of the smaller matrix Q is also the spectral radius of the original matrix. So using this kind of tool, we can find the spectral radius of some matrix which are two partible. One example in graph theory we did in our research work, that generalized Peterson graph. So in that case, we have used this theorem, and we can able to find some spectral radius of very larger graph. That means whose orders are more. So this result is also helpful in some cases. Now, I'll come to the stochastic matrix part. But again, let me come back to the example that suppose we have a matrix, some matrix A, which are having constant row sum, right? So a matrix we have that the matrix is having constant row sum. As an example, if we consider the regular graph and its adjacency matrix, we all know that all the rows are having that what is the regularity of the graph, that many ones, others are 0. So that kind of adjacency matrix of a regular graph will have constant row sum, and which is the regularity of the graph. We can think that matrix in this way, that it has an equitable partition with only one set in the partition. That means the pi is equal to only x1, because we have only one block, that is the whole matrix, and whose rows is 1. And we all know in that case the adjacency matrix spectral radius is the regularity R. Now if we apply this result, you can also now verify that this result, we can merge with this result and that concept, that the spectral radius of a non-negative square matrix A, which we consider a regular graph of regularity R, the adjacency matrix of that kind of graph, and the spectral radius of the quotient matrix. In that case, the quotient matrix is of order 1 by 1, and which is the regularity R. So 1 by 1 matrix spectral radius is R itself. So we can verify this result with that. Now again, stochastic matrix, come to that. We know that a stochastic matrix whose entries are non-negative and for which each row sum equal to the 1 is known as stochastic matrix. That means a stochastic matrix is a non-negative matrix whose entries are either 0 or some number between 0 to 1. That, and also we know the sum of each row of the stochastic matrix is 1. Therefore, stochastic matrix is also can be considered to have an equitable partition with one partition set, and by this result, by this theorem, we can say 1 is the spectral radius of stochastic matrix. So this result is also verified. We all know that spectral radius of a stochastic matrix is 1. So this two example, I think, and this concept is basically the generalization of this concept, that if the matrix have constant row sum is a one eigenvalue of the original matrix. So this equitable partition concept is the generalization of this kind of result. And also, let me tell in that point only that equitable partition, I have worked in my PhD work, but the idea of the result what I am going to present today, I got it from one presentation by Dr. Anirban Banerjee, and he and Ranjit, they did some work. From there only I got the idea and we did it. So I don't know whether Ranjit and Anirban sir is present here. So, but I got the idea from them on. Okay, next. Till now, I said that the eigenvalue of the matrix Q are also the eigenvalue of the matrix A. 3 matrix in this example, but A is a 6 by 6 matrix. What about other eigenvalues? Right? I said 3 eigenvalue of the matrix Q are also eigenvalues of A. But what about the other three eigenvalues of the matrix A? Because and also Q may not contain all the distinct eigenvalues. Sometimes it will contain also all the distinct eigenvalues of the matrix A. I will come to that point later. But here, my next result, what I am going to show that what about the other eigenvalue of the matrix A which are not in Q? So what is that? Let Q be a quotient matrix of any square matrix A corresponding to an equitable partition. The same concept. Also C be a characteristic matrix of phi. That means characteristic matrix, but I have defined. And alpha be an index set which contain exactly one element from each xi. So what does it mean? That x1, x2, xk are the partition set for the actual set x, and alpha be an index set which contain exactly one element from each xi. So alpha will contain k number of elements, right? Because it contains one element from each xi. Then the spectrum of A is equal to the union of spectrum of Q and spectrum of Q star. Now that part we know already is the union of spectral of Q, that we know because all the eigenvalues of the quotient matrix are also eigenvalues of the original matrix. Now here it comes, that spectrum of Q star. So other eigenvalue of the matrix A will be lying in the complement matrix Q star, where Q star is equal to A of alpha complement minus, that means some calculation you have to do, that is nothing but some addition, multiplication, this concept. So we have to take the submatrix of the original matrix depending on alpha, then the characteristic matrix, and in this way we can find the matrix Q star which will contain the other eigenvalue of the original matrix. So this proof I am not going to share. If someone is interested, they can go to the, I will show the reference where you can find the result proof. But here the good thing is alpha be an index set which contain exactly one element from each xi. Now xi we may have some more than one number of elements. So we can have all kind of possible alpha for which we will get one Q star, right? So and we will have mod of x1 into mod of x2 into up to mod of xk number of alpha possible choice we have, and for each alpha we can have one Q star which will contain all the eigenvalues of the matrix A which are not in Q. I will come up with an example there. I think it will be more clear. Consider this matrix, the matrix S, which is actually a stochastic matrix, but you consider it as a matrix, non-negative matrix, and we can able to partition the matrix in such a way so that each block will have constant row sum, and then this partition x1, x2 is the equitable partition for the matrix F, where x1 is 1, 2 and x2 is 3, 4, 5. Then the corresponding quotient matrix is Q. Now we know from the previous result that eigenvalues of Q are also the eigenvalues of X. Now what about the other eigenvalues? Other eigenvalues are the eigenvalues of all these matrices. Suppose Q alpha is equal to 1, 3. How we got this alpha? One element from x1, that is 1, another element from x2, that is 3. So alpha equal to 1, 3. For that we got a Q star. Maybe we have written it as a Q alpha star. So one matrix. Again alpha is equal to 1 and alpha is equal to 1, 4. One element from x1 and another element from x2. For alpha equal to 1, 4, we can have this is the matrix. Similarly, for all possible choices, we can have 1, 1, 1, 1 matrix. And by the previous result, all the eigenvalues of S which are not in Q are the eigenvalues of this matrix. This matrix. Now, what is the where we'll use it? So not only one matrix, we are having more than one matrix, from which we can able to get the other eigenvalue. Now, why we are I am very much stressing on that point that we can have more than one number of this complement matrix Q star. That will be helpful to some other cases. I will later I will tell you. just after a few slides. One more observation. Now, whatever result I said that constant row sum, many times I said, but this we know that if a matrix is there, then its transpose matrix will also have the same eigenvalue, right? Now, if we can able to partition a matrix whose so all these result will also helpful if the matrix have that in case of column it will happen. Now, see this matrix A, it has some speciality. We have partitioned the matrix in such a way. It has some speciality. Can someone got the speciality? What is that? This partition of the matrix A has some speciality. So we can see that rows are constant for each of the block, right? Anything else? Can you see?
Columns.
Anyone from the research scholar? I'm just expecting. Anyone?
Column sum also constant.
The column
Yes.
sums are constants.
Exactly. So this matrix A has some partition. That means it's all the blocks have constant row sum. But for that matrix, all the columns are also constant. This is the beauty of this partition for this matrix. Now, Q equal to if we take the row sum ones and if you take all the constant row sum, we can find the quotient matrix Q equal to this. And if you take the transpose matrix A, then if you take the row sum, we'll get this is the matrix, quotient matrix, right? Now, one may think that, okay, for the same matrix, if we are getting row sums are also constant and column sums are also constant, and we are getting two different matrices P and Q, so shall you get the eigenvalues are different eigenvalues? So shall you able to explore some new eigenvalues if we have this kind of partition where column sums are also same? The answer is no. We can able if we have the same partition set. That means if we have the same blocks and whose row sums and column sums are constant, then maybe we can get different eigenvalues, but it can be proved that they are similar. So this is another result defined in theorem 4. So the eigenvalues of the matrix P and Q are same. Actually, they are similar. If you see the result, you can see they are similar. So we cannot able to get something different eigenvalue. The whatever eigenvalues we can get it from Q, we can get it from P also. But note that I'm saying that the same partition set. Okay. Now,
So here, pi is equitable in terms of columns also. In the
exactly, pi is equitable in terms of pi is equitable for the matrix A transpose as well. And for the same pi, if you get two different quotient matrix, but that means for column one quotient matrix and for rows one quotient matrix, then eigenvalues for both the matrix will be same. We cannot able to get new eigenvalues. Now, till now, whatever we have said, the eigenvalues, the actual eigenvalues we talk. Now, suppose we have a bigger matrix A, which may be of order 100 by 100, and we have a quotient matrix of order 2 by 2. As I said, for the case of generalized Peterson graph, this kind of cases will also come. So, eigenvalues of this matrix Q is very to calculate because it's a 2 by 2 matrix. But the leftover matrix, that means the Q star matrix, will be of order n minus 2. So, many cases it's very difficult to find the eigenvalues. So, what we did that we find the eigenvalue localization for them. So, we find some region where the eigenvalue will be like the other eigenvalue. For that, we want to share a very good classical result, well-known result for the eigenvalue localization theorem. What it says, let A equal to Aij, a square matrix of order n, which may be a complex matrix even. So any matrix of order n by n. Now consider the Gauss-Corin disk. How we construct the Gauss-Corin disk? Consider each rows. Suppose consider the row ith row of the matrix A. Consider the diagonal element aii. So by taking aii as center and all the other entry of the row, that means except aii, all the entries, and if you take the modular sum, and if you take that is as a radius, so for the ith row we can construct a disk with center at aii and the other modular sum of the other entry as radius. We can construct a Gauss-Corin disk corresponding to the ith row. Then for each row we can have one disk. So for a n by n square matrix we can have a n number of Gauss-Corin disks. So we defined it in this way. Now if we plot this disk in the complex plane, then the Gauss-Corin disk theorem says the eigenvalues of the matrix A are in the union of the Gauss-Corin disk. That means, just see this picture. Suppose we have a 7 by 7 matrix, and how we got this 7 disk we have, how we got them. So that consider this circle, or maybe this bigger circle. It has some center, maybe a11, a22, or any diagonal element, and its radius is the corresponding other entries of except the diagonal modular sum. In this way, for each row we can have one disk. So 7 disks we got. Gauss-Corin disk theorem says the eigenvalues are lies within this disk only. So all 7 eigenvalues will lie within this regions only, right? So it's the union of all the region. So if you take the union of all the disks, all the eigenvalues of the matrix A will lie in this region. This theorem also says it has another part also. I have not written, but I can say that if there are some overlapping disks, suppose in this case there are 3 disks, they are overlapped. So in the whole region they can have 3 eigenvalues. In this case it is 2 overlapping region, we can have 2 eigenvalues. In this case they are distinct, they are not overlapping with anyone. So we have only 1 eigenvalue in this disk, we have 1 eigenvalue in this disk, right? So from this theorem also we can say that if some matrix have the disk in such a way that they are distinct, they are not overlapped at anywhere. So we can say all the eigenvalues of that matrix are distinct from each other. Okay. So this is a very beautiful result, very easy to understand, and it's a classical result as well. So if you see the Horn and Junction book, it has a whole chapter with this kind of result, a similar kind of result, but this is the more familiar, useful, and easy. Another result are there, Broward region, Stochastic region, all these kind of results are there. If someone interested, they can go for that Horn and Junction book. Now, what we have used, where we have used this result in our result for eigenvalue localization problem, let me tell that fact. So before that, as I already mentioned that for some cases, whatever result we have for rows, even if it is for the A transpose, all the result is also helpful. Now for the Gauss-Corin disk theorem, the matrix we have considered the rows only, right? Constant the other row sum and this, and we have find some region union of that GA is the region which we got the Gauss-Corin disk by considering the rows. But if we consider the same theorem for the A transpose, we will get different disks, right? We may not get the same disk, we can get different disks, and we can again find for another region where all the eigenvalues will lie. And finally, what is the conclusion? That if you take the intersection of these two regions, that means Gauss-Corin disk, union of the Gauss-Corin disk by taking the rows, and also union of the Gauss-Corin disk by considering columns, both the regions eigenvalues will lie. So in the intersection also they will write. So we have just take that concept. So this is GA is this capital GA is the intersection of two regions. So one is by considering the corresponding this union of the corresponding by considering rows, and this is the by considering union of the corresponding this by considering the columns. Now again come back to our equitable partition. Suppose Q be a quotient matrix of any matrix A corresponding to an equitable partition phi is equal to x1, x2, xk, and let C be the characteristic matrix of phi and alpha I equal to alpha, the index set, and GA is the region defined as in 1, then the eigenvalues of A lie in this region. Now what is the concept? We have already said in case of some matrix have some equitable partition, then the eigenvalue are the eigenvalues of the quotient matrix Q and the eigenvalues of the matrix Q star. And also we said that Q star is depending on alpha. We have many choices of alpha. For each alpha we can have one Q star. For that Q star we can have this region GA by considering rows and columns. Now again we are considering, as I said, that for each alpha we can have a one Q star. For all the Q star will contain the other eigenvalues of that. And what we did, that all the Q star we take and we consider the Gauss-Corin region and we took the intersection. Now can you imagine that how many matrix we are getting, and all these cases we have applied Gauss-Corin theorem and we are getting one region, and finally we have taken the intersections of all the region. So eigenvalues of the matrix A which are not the eigenvalues of the matrix Q are lie within that region. So by applying this technique we have found this region. That what is the concept, that it's clear to us. Just let me come back to the same example. I will come back to the one example. So before that, as I want to mention that that result I was talking about, that Dr. Anirban Banerjee and Ranjit, they did this kind of result, and I said that I got the idea from them. So I have simply generalized their result. So and also there are some other eigenvalue localization theorem for the stochastic matrix. So this is in 2011 there is a result, in 2014 there is another result, and 2016 Ranjit and Dr. Banerjee did this result. Now one thing I can say that here they have considered in this result, they have considered only the rows, and in our case we are considering even columns as well. So we are taking the intersection. So anyway we'll be getting, even for stochastic matrix we will be getting at least same or smaller kind of region. So, and as I mentioned that for the case of stochastic matrix the result will come up in this particular form, this one. And as I mentioned in Horn and junction there are other results also, that if Eigenvalue localization theorem, that's Ostrowski or Brauer. So using that result we have found this result. I'm not going into the detail. I just want to mention this this example, that we have considered a stochastic matrix. Now this matrix I have already shown. It has, first of all, it's a stochastic matrix, and we can clearly see that this matrix have constant row sum 1, right? So we have a partition set, one partition set only, right? So pi is equal to x11, which will contain all the elements, because row sum of the whole matrix is constant, so we can have a single block. But this stochastic matrix has something else. It is not only one partition, you can also able to partition in two partition set as well. I have already mentioned it in previous slide. So if you take this partition and this one, so you can see that this block has constant row sum, this block also have constant row sum, this block has constant row sum, and this block has constant row sum. So corresponding to different quotient partition, we can have two different quotient matrix. One is Q1, Q is 1, that means the actual one, because it's a stochastic matrix. And another one, as I said, it's a speciality. You can also partition the matrix in two sets, x1 and x2. So using that partition, you can have quotient matrix Q dash equal to this. Now what we did, we just plot the eigenvalues, and we can just trying to see that how it is helpful. So this is a suitable matrix. From that we can able to see that these results are localization theorems are very much helpful. Now this matrix is of order 5 by 5 values. They are first one is 1 that we are not considering now, but the other eigenvalues are 0.18 and this one and this one. And from that Q, as I said, that from Q we can have one eigenvalue which is 1, and Q star also one eigenvalue is 1 and another eigenvalue is 0.18. But the other eigenvalues are this. What we did, we plot all the 4 eigenvalues except the matrix point. So if we plot them, then we can see these points are the eigenvalue, actual position. Now we have shown some result, right? This result from theorem 8, theorem 7, 8, 9, and then our result, all this result we have done. So we plot the region according to this theorem. So if you use that in theorem 7, we can see the eigenvalues of the stochastic matrix other than 1. That theorem will give this is the region where the original eigenvalues are lies in this. And if we apply the another result, theorem 8, we can see this result. And if we apply Dr. Banerjee and Dr. Ranjit's result, so if we, that is actually base result, if we apply this result, we can get this is the region, right? And as I said, that if we simply take, for the case of stochastic matrix, if we simply take also the columns, and if we take the intersection, we are getting even much smaller region. That is, even we are taking the intersection, by default it should happen. At least it can be up to that, or in many cases it will be smaller than that. And also for this matrix, we said that it has another equitable partition, and this matrix. So if we left that one eigenvalue 1 and another one 0, 1, 2, and if we consider only these 3 eigenvalues, then according to the general equitable partition result, we can say that eigenvalue will lie within this smaller. Now can you see that how much smaller region we are getting by applying this result? So in this way, these results are helpful. Now, okay, I just thought, okay, let me I tell some of the problem what I thought one may also think. Also, if you are getting some idea, you can also explain to me. You can also tell me. In this way, we can also start some collaborating work. We can exchange our idea one by one. So what I thought that I already said that we have worked on equitable. We have worked on distance regular graph and equitable partition even before this result came. And we noticed that in some cases, in case of distance regular graph, that equitable concept is already used for the finding the eigenvalue of adjacency matrix, finding the eigenvalue of the distance matrix. And there, what happened, that quotient matrix, which is a much smaller matrix, and its order is of d plus 1 by d plus 1, the quotient matrix. Whatever may be the order of the original matrix, adjacency matrix, or maybe the distance matrix, but we will get a quotient matrix of order d plus 1 by d plus 1. And in that quotient matrix will contain all the distinct eigenvalues. That result has already proved. So if you want, you can also go through this reference 3 and reference 2. So where that quotient matrix concept is already there, and you can see that one quotient matrix we are getting there, which will contain all the distinct eigenvalues. Now, then I also thought, okay, then what is the thing that, or what are the conditions that quotient matrix will also contain all the eigenvalues, distinct eigenvalues? But as I said, that in this case they are containing all the distinct eigenvalues. But this is not the case for all. Mostly this is not the case for all. There are some special cases where it is happening. Again, if we consider the simple one, the J by 1 by all one matrix J of order 3 by 3, we can partition the matrix in any order, right? So it's a, if we take one partition set as 1, and it's a constant row sum, so one quotient matrix will be 3. Another one, if we consider that two partition set, one is x1 contain one element and x2 will contain two elements, then we'll get, this is another quotient matrix Q2. Now the matrix J has eigenvalues are 3 and two other eigenvalues which are 0, 0. So from the quotient matrix Q1, we are getting only one eigenvalue, which is 3. But from the quotient matrix Q2, we are getting both the distinct eigenvalue of the original matrix J. So which is 3 and 0, right? But in case of Q1, we are not getting. So generally one can think that what are the conditions on the matrix Q, quotient matrix, such that Q will contain all the, so wherever possible, the quotient part, that equitable partition concept possible, wherever it is possible. So what is the necessary and sufficient condition that Q will contain all the distinct eigenvalues of the matrix A? So this result one can think. Okay, so these are the results. So the whole result I present, you can find it from this reference, and the distance regular graph, as I mentioned, that quotient matrix will contain all the distinct eigenvalues. From this result one can find. And these are the book that Brouwer and Cohen book. There you can find the distance regular graph, and Brouwer and Hammer's many spectral related result for graph, you can find it. And this is the good book, as I mentioned, Horn and Johnson book. This is the result, as I mentioned, that Dr. Banerjee and Ranjit. So their result I got it there, and as Anirban sir presented in Sikkim, so there I got the idea. So you can also see this paper, and these are the other eigenvalue localization results. Okay. Thank you for your kind cooperation.
Okay. Okay. Thank you, Fouzul, for the interesting talk. Yeah. So, audience, if you have any question, you can ask now.
Hi.
Yes.
I have a question about this. When there are more than one ways to give an equitable partition, so you
Okay.
will get different quotient matrices.
Right.
Can we say something about the eigenvalues of each quotient matrix? Will they be related to each other? Or
Okay. So
same as each
first,
other? Yeah.
right. So first of all, if the original matrix A is non-negative, then at least one eigenvalue can say they will be common to each of the quotient matrix, right? Because we said we have shown one result, right? That where if the original matrix is a non-negative one and we are able to find a quotient matrix, then the quotient matrix will contain the spectral radius. So in both the cases, spectral radius will be common.
Yes.
But other thing, I did not think. Maybe one can think other. What about other?
Okay. And another question. Can we say? Can we see whether the quotient matrix also has an equitable partition once we get it?
Yeah, we can have even the example what I shared. You can see that this quotient matrix has also a equitable partition, right? And
Yes.
its
Yes.
quotient matrix is Q1,
Yes.
right?
So, is there
It may
a
not be the
set
case
of
for all.
okay? Is there a set of matrices that would satisfy this property that the
Yeah.
quotient
So
matrix is also equitable, and maybe in a chain it goes on, the
okay.
next quotient is also equitable, and so on.
There I did not think of this result, but see, first of all, our aim should be how means how big this quotient matrix we are getting, right? But how, not how big even. The original matrix is suppose 100 by 100, and if we are getting a quotient matrix of order 4 by 4, then that is reasonable.
Yes, of
And
course.
and if you are partitioning this quotient matrix that 4 by 4, and if you are taking the smaller one, so it will give even less number of eigenvalues, right? So this way I am thinking that. But one may also think of that, what as you are saying. So I don't have that result, but one may think of it. Yeah.
Yes. Do you any other questions? Okay.
I think Rajesh, I just want to thank you for organizing this
Oh,
seminar,
okay.
and I also want to thank the speaker. It was a very wonderful and clear presentation. After a long time, I also could see some old familiar faces. So thank you, Rajesh, for bringing all of us together here.
Thank you, sir. Yeah.
Thank you.
Okay, yeah. Thank you all.
So shall we leave the meeting, sir?
Yeah, we can end the meeting now,
Yeah.
Fouzul. Yeah, thank you so much,
Yeah.
Fouzul.
We'll meet in. Yeah. Thank you very much, sir. Again,
Yes.
we'll meet in the next week.
Yes, yeah. So
And
next
I
week.
hope, as I said,
Yeah,
that
yeah.
which is very much helpful. I am also expecting that
Yeah.
we'll learn a lot.
Yeah.
Thank you.
Sure. Next week,
Uh,
Professor Sivaramakrishnan from IIT Bombay will give his lecture.
Okay.
Krishnan from IIT Bombay.
That
Yeah.
will be good.
Yeah.
Okay.
Okay. Yeah.
Thank you, sir.
Yeah. Thank you. Thank you so much. Yeah.
Thank you. Thank you.
Yeah.